Now, I bet you've all been wondering, well, when does standard deviation and mean come into this? We've been doing it with everything else, and well, it comes in right now. We can find the mean and standard deviation for binomial distributions also. So, when we describe a distribution for binomial random variables, just like any other distribution, we think about SOCs: shape, center, spread. Outlier isn't as applicable for this. So we're going to look at x equaling the number of children with type O blood in a family of 5. We calculated some of these in the previous video. Here's our probability distribution as a histogram. Shape, we're skewed right. It's more likely to have 0, 1, or 2 children rather than larger values. Center, the median number is 1. And we can use our formula for a probability distribution to find the mean. Xi times Pi, so we multiply and add things together. Our mean is 1.25. Cool. Our spread, we talk variance and standard deviation. Our variance, we have that formula. We can do our calculations. We get that the variance is 0.9375. So our standard deviation is 0.968. Cool. There we go. Shape, center, spread. But there's got to be a better way. Well, there is for a binomial distribution. Good news, right? This is special. We've got special rules. So the mean can be found another way. Each child has a 0.25 chance of inheriting type O blood. We'd expect 1/4 of the 5 children to have the blood type. That is, the mean is 5 times 0.25, or 1.25. The mean of a random variable x that's binomial distributed is n times p, number of trials times the probability of a success. The standard deviation of that random variable is the square root of n times p times 1 minus p. So the number of trials times probability of a success times probability of failure square rooted. That's our standard deviation. The formula is much, much smaller and simpler for a binomial distribution. And that's kind of nice, but they have to be binomial distributions. If they're not, these two formulas are irrelevant. So, let's do an example. We've got Mr. Bullard's AP Stats students. They did an activity where they were telling whether or not water was tap water or bottled water. And each one has a 1/3 chance of correctly identifying the type of water by guessing. We're going to let X be the number of students who correctly identified the cup containing the different type of water. So there are 3 cups in front of them. One of them is a different type of water. The other 2 are the same type. So 1 tap water, 2 bottled water. That's how this scenario is playing out. This is a binomial random variable. The number of trials is 21. Probability of a success is 1/3. Each trial is independent. We're going to pretend that the students don't, or we're not pretending, the students aren't going to help each other. Just because one student picked one thing doesn't mean the next won't pick something. So we have this binomial distributed random variable x. The mean will be 21 times 1/3, or 7. We'd expect 1/3 of his students to guess correctly. The standard deviation is 2.16. The interpretation of that is if we repeated this activity many times with groups of 21 who were just guessing, the number of correct identifications would differ from the mean, an average of 2.16. So, what do we use this for? Well, we use this in statistical sampling. When we want to make inferences, educated guesses for lack of a better word, about a population of stuff. So, suppose 10% of CDs have defects. They're not going to harm, or they can harm computers. So 10% of these CDs have some issues, and if we put them into a computer, they'll cause issues. We don't want that, right? We're making CDs. That would be bad. So we can't take every one of these 10,000 CDs and test them. It's just not financially possible. And it would be a very poor business model to test every single one of them. We'd lose a lot of money probably. So we're going to do a random sample in SRS. We're going to pick 10. And this is almost a binomial. What's the probability that x equals 0? That is, there are no defects in those 10. Well, the probability of getting a defect on the first CD, or not a defect, sorry, would be 9,000 out of 10,000. 10%, in other words, 1,000 are defective, 9,000 are good. And we're sampling without replacement. That's why this isn't quite a binomial. These probabilities are dependent on each other. So we're multiplying them together, we get 0.3485. It's important to note that this is not a binomial because we are sampling without replacement, therefore the trials are not independent. But let's say it was a binomial. Let's see what happens. Probability that x equals 0, 10 choose 0 times 0.1 to the 0 times 0.9 to the 10, we get 0.3487. And you know what? That's awfully, awfully close. And in practice, a binomial distribution is going to be a good approximation. It's going to do a really, really good job as long as we don't sample more than 10% of the population. That's important. If our sample size is less than 10% of the population, we can answer these types of questions by using a binomial distribution. If not, we have to approach them as being dependent trials, and the probability calculations get more complex. So to formalize this, when taking an SRS of size n from a population of size capital N, we can use binomial distribution to model the count of successes in the sample as long as that number, that sample size, is less than or equal to 1/10 of the population, capital N. As n gets bigger, as the sample size gets bigger, what do you think happens? We get better information. As we sample more and more data, so here we sample 10, here I sample 20, here I sample 50, what do you notice is happening? I hope you're jumping up and down in your chair saying, it's normal, it's almost normal, it's looking like it's a normal distribution, it's so exciting. And you're right. The more trials we do, the closer we get to a normal distribution. So suppose that x has a binomial distribution with n trials and a successive probability p. When n is large, the distribution of x is approximately normal with the mean and standard deviation as we previously talked about. And as a rule of thumb, we'll use the normal approximation when n is so large that n times p and n times 1 minus p are both greater than or equal to 10. That is, we expect the number of successes and failures to both be at least 10. So here we have a survey that shows fewer people enjoying shopping than in the past. Darn, I hate shopping personally, but to each their own. A survey asks in a nationwide random sample of 2,500 adults, ask if they agree, I like buying new clothes, but shopping is often frustrating and time-consuming. Suppose exactly 60% of residents would say agree if asked the same question. X is going to be the number in the sample who agree. So is this binomial? Let's verify that this is binomial so we can estimate the probability that 1,520 or more agree. So we look at bins. Binomial, yes, we have successes and failures, agreeing and not agreeing. Independent, so this isn't necessarily independent, but we're sampling 2,500 out of 25,000, so we can treat this as if the replacement condition is met. So we are talking about n being less than or equal to 1/10 of our population. N equals 2,500. There we go, a fixed number of trials. And the probability of success is 0.6. Cool. So it's binomial. The only little tweak is with the independence, but our sample size is sufficiently large. Or I'm sorry, it's sufficiently small compared to the population. It's less than 1/10. So to test if we can use a normal distribution, we have to check n times p, the number of successes we're expecting, and the number of failures, n times 1 minus p. 1,500, 1,000, those are both at least 10. We can use a normal distribution. So probability that x is greater than or equal to 1520, we need the mean, we need the standard deviation. We draw a bell curve, ladies and gentlemen, and using a z-score, we find the z-score is 0.82. We can look that up in the table. We look up 0.82, we get 0.7939. That tells us the probability that's less than 0.82. That's how we use our table. We do 1 minus that for a probability of 0.2061. And remember, ladies and gentlemen, we could use our graphing calculator to do this same normal distribution calculation. But the important thing is, before we can do this sort of thing, we have to make sure that our random variable is binomial and that we can use a normal approximation. That is all for today. Have yourselves a delicious and wonderful day.